Hey guys, Mr. Long Break here again. I hope you had a fantastic spring break. We're going to get back after it and we'll start in on ideal gas law. This will be the sixth and final gas law that we're going to talk about in this unit. So after this set of notes, it's pretty much just review until our assessment on Unit 9. So first thing is the formula. And the formula for the ideal gas law is P times V equals N times R times T. And before I start into explaining what each of those variables are, let's talk about when we use this gas law. We use this gas law when there is one set of conditions. And that's very important to distinguish when to use this gas law compared to all the others. And unlike all the others, this is one set of conditions. And what I mean by that is the other gas laws had initial pressures and ending pressures, initial volumes, ending volumes, initial amount of moles, ending amount of moles, or initial temperatures and ending temperatures. But this does not. It just has one set of conditions. And so let's talk about what each of those variables stands for. P is pressure, and that's nothing new. Those units of pressure can either be atmospheres, millimeters of mercury, kilopascals, pounds per square inch, or torr. And so those are our units of pressure. Those are all found on the back of our periodic table. The next one is V, and that stands for volume. And what's different about this gas law compared to all the others is this has to be in liters. So our volume for the ideal gas law has to be liters, not milliliters. And in the other ones, it did not matter as long as they matched. So this has to be in liters. And the way you get from milliliters to liters is dividing by 1,000. Next, we have N, which is moles. And before we get to that R, that fancy new one, I'm going to go ahead and label T. T is temperature. And just like all of our other gas laws, it has to be in Kelvin, and we do that by adding 273. So now I'll get back to this new fancy variable, R. And R is the gas constant. And the good news is this gas constant can be found on the back of your periodic tables. However, you have to distinguish which of the three gas constants you're going to use. There are three different gas constants, and they're either 0.08206, 8.31, or 62.36. And if you notice, the only difference between these numbers and their units are the units of pressure. And that's exactly how you're going to decide which of those R values to use. So your gas constant or your R value has to match the units of pressure. And so quickly I'm going to scroll back to our formula, and underneath the gas constant I'm going to add that important piece of information. It has to match the units of pressure. So now that we have that formula, let's go ahead and try to solve a few problems. Our first one is changed slightly from the notes page on page 22, but it's pretty much the same. So I'm going to read through this and label all the variables, and then we'll go ahead and try to solve. It says, it is not safe to put aerosol canisters in a campfire because the pressure inside gets very high and they can explode. If I have a 1 liter canister, so that's a volume, 1.0 liters, that holds 2 moles of gas, that's N, or moles. And the campfire temperature is 1,421 degrees Celsius. What is the pressure inside the canister in atmospheres? So we're looking for pressure. And if we look through these variables, we have everything that is in our ideal gas law except our gas constant. Our ideal gas law, remember, is PV equals nRT. So we have pressure, that's what we're looking for. We have a volume, we have moles, we have temperature. We need to go ahead and label our gas constant. And to label our gas constant, we need to look at the units of pressure. We are finding pressure, but it wants the pressure in atmospheres. So I'm going to look at the periodic table at the back, and I am going to look for the R constant that is in atmospheres. And if I look, This is the R constant that has the unit of atmospheres. So that is the R constant that I'm going to use. So I'll scroll back here and I will go ahead and label our R. R is going to be 0.08206. And I'll put atmospheres just so we know that that is the unit of pressure there. So now I'm going to check all my other units and make sure they are correct. Volume has to be in liters. It is in fact in liters. Moles is good. And then my degrees Celsius has to be in Kelvin, so I'll go ahead and do that. I add 273 and I get 1,694 Kelvin. This goes to the ones place, so I need to make sure my Kelvin goes to the ones place. It does. So now I'm good to go ahead and plug this into our formula. So we have P, which is what we're solving for, times V, which is 1.0, equals N, which is 2, R, 0.08206, that's our gas constant, times T, which is 1,694. So now we are ready to solve algebraically, and what I'm going to do first is I'm going to simplify the whole right side of the equation. And so when I do that, I get P times 1.0, 278.01928. So I'm not going to round yet. I'll wait till the very end to round. And then next, I will divide each side by 1 to get P by itself. And anything divided by 1 is just itself. And so I'm going to get P to equal 278.01928. Last thing is to check for significant figures. If I look through my problem and my initial numbers, we have 4 significant figures. This is a constant number or an exact number, so we are not going to use that for sig figs. Our volume had 2 sig figs, but our moles only has 1 significant figure. So I'm going to go ahead and round this to 1 sig fig, and it is going to be 300 atmospheres is our unit of pressure that it wanted us to solve for in the equation. So that's our final answer for the first one. Pretty straightforward. We're going to go ahead and do example number 2 now that is a little bit tougher. Example number 2, let's go ahead and start with our variables again. It says how many grams of oxygen are in a 0.500 liter, so that's volume, 0.500 liter, sample of gas on top of Mount Everest where pressure is equal to 525 millimeters of mercury. So I'll go ahead and label that as my pressure, 525.00 millimeters of mercury. And the temperature is 254 Kelvin. And so it is looking for grams in this particular equation. Well, if we look at our ideal gas law, PV equals nRT, none of those variables stand for grams. However, if I were to pose the question, which of those values can get us grams eventually, hopefully we would come up with the answer of moles. We're used to converting moles to grams. So even though that this question is asking about grams, if we get moles, we can then do a final step where we convert moles to grams by using molar mass. So I'm going to go ahead and write in N here. That is the true variable that we are solving for here first. And then the only thing we're missing is our R constant. So if I flip back to the back of our periodic table, here our unit of pressure is in millimeters of mercury. So this time the R constant that I'm going to use is 62.36. So I'm going to go back here and label the R constant as 62.36 millimeters of mercury. Okay, so now I'm going to go ahead and plug in our numbers because our volume is already in liters, our temperature is in Kelvin, our pressure is good to go, and I found the correct R constant. So P, which is 525.00, times volume, which is 0.500, equals N, that's what I'm looking for or solving for, times R, 62.36, times T, which is 254. Okay, so now I'm going to simplify and solve for n algebraically. First thing I'm going to do is going to go ahead and simplify both sides of the equation by multiplying those values together. And so on the left side of this equation, we're going to get 262.5 when we multiply 525 by 0.5 equals n times, when I multiply 62.36 times 254, we get 15,839.44. And I'm going to make sure I don't round until the very end. Then next, I'm going to go ahead and divide both sides by 15,839.44 to get n by itself. And so when I do that, we get n to be equal to 0.0166 moles of oxygen. Now, I made sure to round to 3 significant figures because volume has 3, the pressure had 5, the temperature has 3, and this is an exact number. So the least number of sig figs is 3, and that's why I rounded our moles to 3 significant figures. Now, we're not done, and that's because, remember, the initial problem was asking for grams. And so we have moles, but we need grams. And so the final step is going to be to take this number of moles and convert it to grams. And so I have 0.0166 moles of oxygen all over 1 times moles of oxygen go on the bottom of my next ratio, and I'm going to convert it to grams of oxygen. And if we remember, the way we do that is by using molar mass. And so if we look on the front of our periodic tables at the mass of oxygen, it's 16, and this is O2. And so the mass of 1 mole of oxygen is going to be 32.00 grams in 1 mole. And the last thing to do is to multiply 0.0166 times 32. And once again, round it to 3 significant figures. I get 0.531 grams of oxygen. And that is our final answer. So whenever you have a question involving grams, remember that grams is related to moles. We can always find grams by getting moles first. And so that is pretty much the most complex problem you'd ever see with the ideal gas law. Now you guys are ready to start some practice and prepare for that Unit 9 test. Let me know if you have any questions. As always, I'll be as available as possible. I miss you guys. I hope all is well.